Hi, this is Peter with CalcBook, and today we're going to be continuing our design of a steel member with Slender elements. And this is going to be part 2 of the series, which is going to focus on flexure and combined loading, and we'll also do a quick check of shear as well. So just a quick recap, right? We're going to be utilizing the AISC Specification, Chapter F, and then we're also going to be using Chapter G for shear, and then Chapter H for combined loading. And a quick review of our problem statement, right? We are designing a collector that has axial load, and then it has distributed load applied about both axes. It's got an unbraced length of 10 feet. It's a W21 by 44. It's A992 steel. And then it's the same loading that we have from the last problem. So I'll put a link in the description below for the part 1 video, and you can take a look at that if you want to get familiar with the rest of the problem statement and the compression design. So let's go ahead and open up CalcBook, and we will continue on this part 2 series of designing a steel member with Slender elements. All right, we've got CalcBook open now, and we're just going to go ahead and open up the file that we used last time. So we're going to start with Slender Elements Part 1, and we will just build off of that. So we've got our Part 1 file open, right, and that's just going to bring in all of our information from last time, so our shape selection, our material properties, and all that sort of stuff. And then you also notice that we've rearranged a little bit of the input pane on the general tab, just bringing the load source and load combination selection up to the top, just for easier access for everybody. But first, we're just going to go ahead and jump right into the beam loading. So our beam, we're going to go ahead and include the self-weight. Our length is going to be 10 feet long. Our analysis location from the end, we are just going to assume the midspan right now, because that will be the worst case scenario. So it's populated the graphs right now with just the dead load, but we need to add in our other loading that we have from our problem statement. So we have a dead load in the strong axis, so we are about the strong axis right now. So we're going to add a dead load of 350 pound per foot, so that's going to be a uniform load. That's going to be 0.35 kip per feet. Save that. And then we have a live load about the strong axis. That's also going to be a uniform load, and that's going to be 0.45 or 450 pounds per foot. Save that. And then we do have a load about the weak axis. So we're going to go click on the weak tab, and this is just going to be an earthquake load, seismic load here, and that's going to be a uniform load. And that is going to be 600 pounds per foot or 0.6 kip per foot, and save that. And it doesn't populate here because you need to change the selection here. The selection of the load combinations here does not affect the design load combinations. That will still automatically be selected based on the critical load combination, but this just allows you to view the different graphs based on the load combination that you want to see. So I think we've got everything we need for the beam design. So now we can go ahead and add in our flexure design. So we can just go to this plus button here, add calculation, and we're just going to click on all of these since we're going to eventually look at all of these items here. And you'll notice that once we add in the flexure design, it automatically populates the combined loading. So it knows that because we have flexure design as well as axial design, it needs to automatically populate that Chapter H combined loading tab. So now we can step into our flexure design about the major axis, right? Our buckling length, it's going to be the same length as the beam, so that's just going to be 10 feet. And then the CB factor, we can take advantage of this, right? We have a distributed load with no restraints, so it's going to be 1.14. And remember, the demand is automatically calculated, right? It's going to be pulling that in from our beam loading tab, so we don't need to do anything here for the demand. Okay, and so then from there we can go and check and look at our beam design. We'll check for slender elements. So the first thing we do is we check the flange, right, and the flange is compact. Then we check our web, and our web is compact. So we only have slender elements for compression for this calculation. So then we can just do our flexural strength per Chapter F2, right? And this is a pretty large beam, so and a pretty short span. So we have quite a bit of capacity in this beam, right? And then we have our design flexural strength of about 300 kip foot, which is controlled by lateral torsional buckling and a very, very low DC ratio. Okay, and the next thing we need to check is our minor axis spending, right? And there's really no other additional capacity factors that we need to add here. It's pretty straightforward. So it just pulls in the weak axis spending demand from the beam loading, and then it goes ahead and checks the weak axis bending based on chapter F6 in AISC spec, and we get a ultimate DC ratio of 0.2. So then once we have that, we can go into the combined loading. We'll come back to shear in a second here. We'll go into combined loading, and we can just open this up, right? And it's going to do the check automatically for us. So the axial DC ratio is greater than 0.2. So we use equation H1-1A, and that gives us a combined DCR of 0.7. And what you'll notice now is that now that we have combined loading open, if we go back and look at, say, the demand calculation, right, for compression, it's going to use load combination 6, right? And then if you look at flexure, it also uses load combination 6 and then minor load combination 6. So all those are linked together based on the critical combination based on the combined loading. So once it figures out this critical load combination running through all the different possibilities, it makes sure to set the correct load combination for all the other designs. So then we can go ahead and do a quick check of shear. Right, we can decide if we have stiffeners or no stiffeners. We're going to say we have no stiffeners. And again, the demand is going to be 0 here because we have the beam loading set to mid-span where there is no shear. But let's say we set this to 0, right, where we have our maximum shear, 0 or 10 feet. And then we can go back into our design, right, and it will pull the correct shear values from that. And our shear is pretty low. It's a pretty big beam, so we don't have much shear here. So that is the part 2 series of our steel member design with Slender elements. One other thing that I wanted to point out here is that we did add a new feature in CalcBook recently allowing you to adjust the level of detail shown in the calculation output. So if you toggle this to simple, right, it will just hide that middle step of the calculation output. So you still see the equation with the variables and then the final answer, but you can just reduce the length of the calculation a little bit by removing this middle step showing the actual values if you'd like. So that gives you that option here where you can toggle those back and forth and decide what you want to see in the calculation output. So we hope you enjoyed this video. We would like to offer you guys a 25% discount. You can use the discount code YTCB2024 during checkout. And yeah, we hope you enjoyed this video, and we'll see you next time.